In this video, we'll talk about one of the main applications of thermodynamics and thermochemistry, and this would be calorimetry. So for calorimetry, what we're trying to do is measure heat transfer. And there's usually two main reasons that we'll do this. So one of the ways that we can do this is to mix two things together, and we'll observe a temperature change. So let's say we mix some hot water with some cold water. We know that the cold water will get warmer and the hot water will get colder as they transfer heat in between the two. So since we're looking at heat transfer, to start these calorimetry problems, we'll use this equation. So the heat that one thing is gaining is going to be proportional to the heat that the other thing is losing. Remember, this comes from conservation of energy, so energy can't be created or destroyed, merely transferred. And if all the energy being transferred is in terms of heat, that means that the heat that one thing is losing has to be proportional to the heat that something is gaining. The other thing you'll notice in here is this change in sign between the two, and this has to do with our sign conventions when we're talking about thermodynamics. So if something is gaining heat, we have a positive Q. The other thing has to have negative Q of the same magnitude in order for energy to be conserved. So let's talk about the first application of this, and that would be determining the heat capacity of a metal or some other solid object. So remember, for ideal gases, we can find the heat capacity just based on the property and kinetic molecular theory of gases, but for other objects, these heat capacities need to be empirically determined. And so one way we could do this is to take a piece of metal that's heated up and plop it in some water, which we happen to know the heat capacity for already, and we can do a calculation. So we can see that the heat gained by the water has to be equal to negative the heat lost by the piece of metal. So the metal is going to lose the heat, the water is going to gain the heat. And so we can add these subscripts for the two. And so far that doesn't get us quite straight to the heat capacity, but we know that we can relate Q to heat capacity using our equation Q equals mc delta T. So let's look at a practice problem. Let's say we have 50 grams of some metal, and it's heated up to 95.4 degrees Celsius. And we're going to add this to 100 grams of water that's initially at 25.0 degrees Celsius. We can measure the final temperature after they come to thermal equilibrium, and we see that this is 36.4 degrees Celsius. We know the heat capacity of water, 4.18 joules per gram per degree Celsius. And so let's look at how we could find the heat capacity of the metal. So to set this up, the Q of the water, again, is going to be equal to negative the Q of the metal. We have our equation, Q is equal to mc delta T. So we get the m of the water, the heat capacity of the water, and the change in temperature of the water will be equal to those, all with relationship to the metal. This is one of the parts to be careful when you're plugging these two equations, that all these values are going to be different on both sides, and you have to make sure that they come from the right species. Okay, so we know that we're trying to find the heat capacity of the metal, so let's start by just solving this for C metal. So to do this, we'll divide both sides by the negative M metal by negative delta T. So we get the heat capacity of the metal is going to be equal to the mass of the water times the heat capacity of the water times the delta T of the water divided by negative the mass of the metal times the delta T of the metal. So we can start plugging these values in. We have the mass of the water, that's 100 grams. We have the heat capacity of the water, 4.18 joules per gram per degree C. This is a good time to check that we are using the right version of this equation. So where we have mass, the heat capacity is in units of mass, so we're good to go. And then the change in temperature. So remember, delta T is going to be T final minus T initial. So we expect this to be positive for water because the water is heating up. So we have our final temperature, which is 36.4, and the initial temperature, which was 25.0, and that's all degrees Celsius. So the top looks good. And for the bottom, we have negative the mass of the metal. So that's up here, 50 grams of metal. And then we have the delta T of the metal. So the metal's initial temperature is 95.4. The final is still 36.4. And we can see, since the initial temperature is higher than the final temperature, we expect this term to be negative, which is good because that means this will be negative overall, That means these two negatives will make a positive, and the heat capacity overall should be a positive number. Heat capacity should always be positive, because physically speaking, a negative heat capacity would mean that if you threw something into a fireplace, it would actually get colder, which just doesn't make sense. And so if we plug in all of these values, these are all the numbers, that'll give us the heat capacity of the metal. In this case, we get 1.62 joules per degree Celsius per gram. We can see if this makes sense sort of qualitatively also by comparing this to the heat capacity for the water. So we can see that the metal actually has quite a vast temperature change compared to the water, but that makes sense because the water has a higher heat capacity and there's more grams of the water. So this looks like a reasonable value. We can look at another application of calorimetry, and this is going to be studying the delta H of a reaction. So there's something we'll note here in this calorimetry setup. So for this type of equation in particular, and what we're going to use, you'll often hear this being called coffee cup calorimetry, because one way that this is usually done in a teaching lab is to take a couple of styrofoam cups, use this to contain the reaction, and then we run the reaction inside, make sure this is mixed, measure the temperature with a thermometer. So we can say that all the heat transfer that's happening is fairly well contained in this insulation. One of the things that's implied in this coffee cup calorimetry, since nothing is sealed, is that this is constant pressure. We won't really look at constant volume, aka bomb calorimetry, so these equations are for constant pressure calorimetry. Why does that matter? Well, if we're studying the delta H of a reaction specifically, we know that delta H is equal to NCP delta T. So this looks very similar to all the heat transfer, but mainly the enthalpy is the heat at constant pressure. And so since we're doing this at constant pressure, this is just another way to measure heat transfer, looking at the delta H of a reaction. So for this kind of setup, we would take something, the reaction that we want to happen, and make it occur in the solution. And so in this case, where we are dissolving something in water, looks like this should be NaNO3. But when we're dissolving something in water, we have our system, which is this equation, and we know that the system will have some related enthalpy, and this is going to be related to the heat that's transferred, and this transfer will all go into the solution. So the temperature of the solution will change, and we can use this to do a calculation. We have to be a little bit careful when we're considering sign conventions for this. So let's think about this question in general. Say we're going to dissolve some solid in water. They're both initially 25 degrees Celsius, and the temperature of the solution or the water is going to decrease. So in this case, if the water decreases, think about the delta H for the dissolution reaction. Something important to note for this is that the system is just the salt dissolving and does not include the solution after the reaction, but just the process of dissolving the salt. Okay, and the answer for this is delta H is positive. So remember, if delta H is positive, this means that heat is a reactant, which also means that this reaction is endothermic. So if we think about this for a second, if the reaction is endothermic, that means that the reaction itself is gaining heat. So this is gaining heat, but you'll notice that the temperature decreases, and that's because in order for this process to be gaining heat, it has to take it from somewhere, and it's going to take it from the solution in this endothermic process. So the delta H of the reaction, if the surroundings get colder, is going to be positive, whereas if the surroundings got hotter, it would be negative. So remember, exothermic reactions have a negative delta H. They'll release heat, but the surroundings will feel warm because they are getting that heat. This would be like a typical combustion reaction, whereas in endothermic reactions, the system's going to have to take heat, so that'll make the surroundings feel colder, and the temperature of the solution will decrease. So let's take a look at a practice calculation that looks at using this type of calorimetry. So here we have constant pressure, 12.5 grams of calcium chloride dissolved in water that's initially at 25 degrees Celsius. We're given the enthalpy of this reaction is negative 81.5 kilojoules per mole. We're given some extra information here that the resulting solution weighs 100 grams, and we're given the heat capacity of the solution. Now the question is what is the final temperature of the solution? Something important to note is that here we have our final mass and our final heat capacity of the whole solution. So this is everything we'll worry about for what's getting the heat transferred to it, and the enthalpy is limited to the reaction itself. So for the setup of this, we have our Q of the final solution is equal to negative Q of the reaction. This is still our Q lost is equal to negative Q gained, or vice versa. And so if we set this up, we have this Q, which is mc delta T. But now on this side, we're going to do something slightly different since we have the enthalpy instead of a heat capacity for this reaction. We're going to use that for the heat of this reaction. Because again, remember, Qp is equal to delta H. You'll notice something else in this version of the equation, that we have an N out front in front of this delta H. And that comes from the fact that, remember, when we have a delta H for a reaction, it has to do with the stoichiometry of the reaction. So if we dissolve more calcium chloride, we'll get more kilojoules. So it's always going to be per mole of the species that we're talking about. If we have two different species and this is a limiting reagent problem, you'd have to look at what we did when we were looking at calculating delta H's earlier on, do some stoichiometry, and find which value actually mattered for this equation. So this N out front, again, is just to remind you that it depends upon the quantity of what's reacting. So let's plug these in. In this case, we have our mass of the solution, which we can use here. So that's our 100 grams. Our heat capacity, 4.18 joules per degree Celsius per gram. And our delta T is what we're trying to find. So I'll write that right here. And we have that this is equal to the delta H of this process. So we need to take the moles of calcium chloride times the enthalpy of the reaction. And don't forget the sign change. So we have negative, and then our 12.5 grams of CaCl2, we need to get that into moles. So 110.98 grams per mole. And then our delta H, which is negative 81.5 kilojoules per mole of CaCl2. And you see we still have one little issue here. This side is in joules, this side is in kilojoules. So we have to normalize one of the sides. And so we can do that by multiplying this by 1,000 joules per kilojoule. So on this side of the reaction, you get 418 joules per degree C times delta T. And on this side of the reaction, you get 9176.9 joules. Dividing both sides, you get delta T is equal to about 22.0 degrees Celsius. And then remember, we have to look at the initial temperature. So delta T is positive, so the final temperature is going to be equal to 25 plus 22, which is equal to 47 degrees Celsius. So we have this answer of 47 degrees Celsius, which is a high temperature. Thus matches the fact that the reaction with a negative sign is exothermic, so we expect the solution to get hotter. Let's look at one more practice calculation where we take 17.5 grams of sodium nitrate. We're given its molar mass. It's dissolved in water to make 100 grams of solution. And then we have the initial temperature of both, the final temperature of the solution, and we want to find the delta H for the dissolution of the reaction. Kind of how this is commonly used to find the enthalpy of reactions. So for the same setup, we have our mc delta T is equal to negative N delta H. And so we get delta H is equal to mc delta T over negative N. And then plugging everything in for the mass of the solution, we have 100 grams. The heat capacity of the solution, 4.18 joules per degree Celsius per gram. The delta T, so this would be our final, 14.2, minus our initial, 25.0, over negative moles. So since we're given a mass, we have to convert that to moles, 17.5 grams. And we have that that's 85 grams per mole. And if we plug all this in, we get 21,900 joules. Or if we're converting to kilojoules, that would be 21.9 kilojoules. And all of this is per mole, and specifically this would be per mole of NaNO3. So in summary, for these calorimetry problems, anytime you're mixing two things together and a temperature change happens, we know that we're going to set these up with Q gained is equal to negative Q lost. So the first thing you want to ask is, does a reaction happen? So are we doing some chemical equation, or is it just heat transferring directly from one substance to another? If the answer is yes, some reaction happens, this is going to be the heat of the reaction is equal to negative Q of the solution. So we have this N delta H is equal to negative MC delta T, or we can put the sign on either side. That's fine. But one side has a minus, one side does not. If it's just heat transfer, that means the heat lost by one thing is equal to negative the Q gained by the other. And so we have MC delta T for one species is equal to negative MC delta T for the other species. So you'll note you can have the minus sign on either side of the equation as long as you always remember that delta T is always T final minus T initial.